I wanted to try to make as short of a video as possible for introductory trig. So if somebody doesn't know what it is or how it's used, and they only have high school algebra skills, then they can see this video and understand quite a bit about trig. And then they could follow along with the rest of my videos where I use trig. This is the kind of stuff I was curious about when I was a teenager, but in order to take a trig class, it was a pretty rigorous class, so you had to be a pretty good student and mature enough to study, which I wasn't. But this is the kind of stuff I enjoyed learning because at one point I learned about tangents and I just thought that was the coolest thing in the world, but I didn't learn anything else about trig. My intention for this video is to make this like the trig version of 7-minute abs. That was a scene in Something About Mary where a guy was going to make a video called 7-minute abs to compete with the 8-minute abs video, and that would work as long as nobody came out with a 6-minute abs. So here we go, basic introductory trig. Keeping in mind this is a 1-semester class, so there's quite a bit more to it than this, but this will get you started. You just have to have high school algebra skills to know how to isolate variables. For example, s equals O over h. S is by itself, bring the h over. Now O is by itself, and then bring the s down, and now h is by itself. If you can understand this, then you'll be able to understand basic trig. Take a right triangle. It has to be a right triangle. It can't just be any other kind of triangle. You have to have that right angle right there. Remember, SOHCAHTOA. So here's your angle in which we're interested right here. Sine of this angle equals opposite over hypotenuse. Opposite divided by the hypotenuse will give you the sine. Cos is adjacent divided by hypotenuse. Tangent is simply opposite divided by adjacent. These are all simply ratios of each other, so it's just one divided by the other. This could be 3, 4, 5, or you could stretch this triangle out and make it twice as big, and then you could have just double each side. You could have a 6, 8, and 10, or whatever. Instead of 3, 4, 5, you could have 30, 40, and 50. It's just all a ratio of one divided by the other. You could take the inverse of these fractions. So instead of adjacent over hype, you could have hype over adjacent, and that would be called the secant. So then this would be called cosecant, and this would be called cotangent if you take the inverse of those fractions. In reality, that's not typically done because that's kind of redundant, but the secant, cosecant, and cotangents are used when you insert these things into larger formulas. So you only have to know 2 out of the 3 right here. You have 3 variables: opposite, hypotenuse, and the angle. So here's our triangle. For the standard unit triangle of trig, they make the hypotenuse 1. Sine of 30, let's say this angle equals 30, that's opposite over hypotenuse. So opposite, which is right here, opposite over 1. Bring the 1 over. Just hit 30 on your calculator, hit sine, and you'll get 0.5. Make sure the calculator is in degree mode and not radian mode. Opposite over 1 equals 0.5, so just opposite equals 0.5. Now we know the value of this leg of the triangle. Instead of using this angle, you can use this angle over here, and then this will become the opposite, and that will become the adjacent. If we know the opposite and the hypotenuse, and we want to find out the angle, you just, the way this works is you divide both sides by sine, so we can get theta by itself. So sine times 1 over sine, that's the same thing as sine divided by sine. So these will cancel out, you're left with theta. And then 1 over sine is the same thing as sine to the negative first. So you end up with sine to the negative first of 0.5 over 1. Hit that in your calculator, just hit 0.5, hit the arc sine button, and it'll give you the angle. In this case, it'll be 30 degrees. This is also called sine to the negative first for obvious reasons, or the inverse sine because it's 1 over sine. So this is the arc sine. There's also an arc cosine and an arc tangent. If you have the lengths of the legs and you want to find out the angle. Keep in mind what's useful about this is that you only have to know 2 out of the 3. So you have to know 2 legs to get the angle, or you only have to know 1 leg and an angle, and you can find out everything else. Here's how we can use this. Just make up a right triangle right here. If a plane's flying along due east at 87 miles per hour, kilometers per hour, whatever, there's a crosswind at 50, then it'll push the plane over to here. This will form an angle of 30 degrees. I keep picking on this angle because it's just easy. You can also use Pythagorean theorem of a squared plus b squared equals c squared. So this works for velocity, 87 miles per hour this direction, plus 50 this direction for the crosswind, gives you a total velocity of 100. Or, since distance is almost the same as velocity, because in 1 hour, you will have traveled 87 miles this direction, 50 miles this direction, and 100 miles that direction. From what I understand, this is also how space probes get a gravitational assist from planets. A space probe will be traveling in that direction. A planet will be traveling this direction as it revolves around the sun. So then this velocity and this velocity are combined with a squared plus b squared, gives a final velocity that's larger than the initial velocity. Remember, with Pythagorean theorem also, it has to be a right triangle. You can also use it to find the height of something. You can take a protractor with the little plastic things you use in math class, tape a straw to the top. The straw is optional. Hang a string with a weight on the end. Just look through the straw at something and use that string to find out what the angle is. If you have a tall tree or a pole or a tower and you want to get the height of that, just stand back, look up at a certain angle, pace off the distance from here to here. Now you'll have your angle and you'll have the adjacent of that angle. Just add an extra 5 feet or so because your eyes will be about 5 feet off the ground. If you use 45 degrees, then no math needed. So what you can do is just walk back and forth until your eyes are at 45 degrees. Then whatever the distance is from here to here will be the same as the distance from here to here, because adjacent will equal opposite. There's a leveling app on iPhones. I assume that other smartphones have a similar app, but you can look over the top of it and it'll tell you the degree at which you're looking up. And this will just be approximate. I actually used this when I had a tall branch in my backyard and I needed to know how much rope to buy to throw over it for a rope swing. It was about 30 feet high off the ground, so it was far too tall to reach with a ladder. And if I didn't get enough rope, then yeah, that would be tough. And if I had too much rope, then I'm just paying for extra rope that I'm not going to use. So I actually used this to get the height of that branch. It was so tall, to get the rope over it, I actually used my bow and some fishing line, shot the arrow over the branch, and then tied that fishing line to some paracord, pulled the paracord over, and then tied the paracord to a thicker rope and pulled the rope over. If you don't use the paracord as an intermediary and you just tie fishing line to the big rope, that big rope's going to have a knot in it, or it's going to snag on the branches as you pull it over, and you'll keep breaking your fishing line. I learned that lesson the hard way. But then I used twice as much rope so the rope could go over the branch, back down, and then I could tie the rope to the tree, and then that way I could raise and lower the swing as needed from the ground. Here's how you can use trig to understand your daily life. Take a board, wedge it between 2 walls. For this experiment, I used a step, like a stair that went upstairs in the wall. I put a wheel there to show that there could be no friction, but in real life, I just laid a board between it. Push down on this with a force of 100 pounds, for example. Then you can redraw this triangle to right here, and this will be 100. And if the distance from here to here is about 5 times the distance from here to here, that'll give you about 500 pounds of force pushing into the walls. You can use your arctan function to just measure the distance between here to here and from here to here, and that'll give you the angle, say 10 degrees for example, and you can start finding out how much force you have pushing down and how much forces you have pushing in different directions. And if this makes a 10-degree angle right here, for example, you can use tan of 10 degrees or tangent of 10 degrees equals opposite over adjacent. You can find out how much force is on the adjacent side of 567. Now the floor itself here, this isn't providing any outward force. It's this board here, the hypotenuse, but this hypotenuse can be divided up into a vertical and horizontal component. 100 pounds is pushing down, so if you had a scale right underneath, it would register as 100, and there's 567 pounds pushing out from this board. So this 567 is equivalent to this leg of the triangle right here. And then you can use Pythagorean theorem if you want, or trig, a squared plus b squared equals c squared, but you'll have 576 pounds pushing up. When I did this experiment, I just laid the board between the step right here and a wall, and I put a bathroom scale up next to it. It had to be an old-fashioned bathroom scale with springs because the electronic one wouldn't work when it's on its side. The electronic ones only worked when they're laid flat, at least the one I had. That's the way it worked. So I just used an old-fashioned bathroom scale with springs, and I pushed down right here with, I don't know, not very much weight, and I got a huge weight right there. I don't remember the exact numbers. But this is how you use this in your daily life. If you're lifting weights, you got a weight here. Here's the forearm, here's the upper arm, the humerus. This could be the tricep muscle. As it contracts, it squeezes on this elbow and straightens out the elbow. If you push in with a force of 100, and this leg right here is 4 times longer, you'll push up with a force of 400. So you've multiplied your force by 4. This works whether it's an elbow or whether this is a knee right here and that's the foot. This could be a quadricep going over the knee. So if you push up with 100, or if your muscle pushes in with 100 units of force, you'll get 400 units pushing up that way. So this explains why when lifting weights, it's much, much easier to barely bend the joint, and you can lift a huge amount of weight. And then if you bend the joint a lot, it becomes very hard. This also partly explains why stairs are only about 8 inches tall. We could step up on something over 2 feet tall if we wanted to, but by making stairs small, then we have a lot of force when we climb stairs. Plus, I imagine there's a safety consideration where the smaller your stairs are, then if you fall down them, it just becomes a bumpy incline slope. If you have great big steps, then you're gonna take a pretty hard hit if you fall down each one. So here I just did a 4-to-1 ratio. What's the angle here? I don't know, I didn't do the math on it, but you can do that with the SOHCAHTOA to get that angle. Here's the other extreme if you greatly bend the elbow. So it's still a 4-to-1 ratio, but now the leg of the triangle that is 4 units longer than that leg, this is the horizontal component. So your muscle contracts and pushes in with 100 units of force. This leg is only 1/4 of the length, so you're only going to get 25 units of force pushing up. Compared to this one, you have 400 units pushing up for 100 units being pushed in, and here you only get 25. Trig is also used for sine waves and cosine waves, which means it measures light waves, radiation waves, or electromagnetic radiation. But that's more detailed than what I wanted to go into here. I just wanted to do something that could show how you can use this to explain your everyday life.